We have two more talks for the day. Teo has one of them on replacing the deep runtime hooks with templates. So take it away.
Okay. Thank you. I've actually given this talk 2 years ago, and now this will be like an update on it to tell you what has changed, what I've learned from these 3 symmetry order of codes, because this has been a project for the last 3 instances of the symmetry order of code, and I've made, I would say, substantial progress with it. And now I want to let you know about all this and what still needs to be done, because there is still some work to do and the changes we're proposing. So first of all, I'm from Bucharest. I'm from the Polytechnic University there in Bucharest. The way I started working on DRuntime is I took this as my master's project, and I worked with Razvan as my advisor for this. So first of all, we'll go over all the 3 main words of the title. So DRuntime, hooks, and templates. First, let's define and put into better context what DRuntime actually is. What does it give us? Well, it gives us support for a lot of cool language features that we all love to use, such as associative arrays. They are implemented in DRuntime. Array operations such as concatenations, but not slices. So slices would still work without the DRuntime, but not concatenations. All sorts of exception handlings. And since exceptions are classes themselves, class support is also provided by the DRuntime. In addition, allocating arrays and to put them all into one bucket. Everything that requires the GC requires the DRuntime, because the GC is part of runtime. So obviously, if you're using beta C, you lose access to all of these because beta C excludes the runtime. So this is what it does. Now let's take one example and see how this is actually being done. We're going to talk about the second word from the title, which is hooks. Say you write a piece of decode, namely this concatenation. What the compiler would do is it would replace this expression with a call to a function. This function is DArrayAppend. This function is called the runtime hook. Basically, hooking works by having the compiler look into the runtime, find the proper function with which to replace some higher level code, and do this replacement. So this is called hooking. And all these functions you'll see are prefixed with a _d_ prefix. Okay, then during linking, the runtime is brought, and then the resulting binary will contain all runtime hooks. Do note that all hooks are contained in the binary despite them not necessarily being used. This is kind of a small nuisance that we also fix with our work, but this is not the main point that we're going to attack. So this is the workflow that we are going to alter. One thing to note is that the place in which all this compiler magic takes place is the IR generator. And if you remember Walter's talk at the very beginning of today, he spoke about the code generator, which uses this intermediate representation. Well, when you move from the AST, which we're going to use a lot, to his intermediate representation, you need some sort of layer, a glue layer, that will convert the AST to Walter's IR code. And this is the one that was previously introducing these hooks. So now we have a high-level view of what's going on. Let's look under the hood. Specifically, let's analyze this hook and see what it does in particular. So this is a slightly simplified version of the hook, but it does the main things that it's supposed to. So first, it takes this extra argument. You would expect it from the previous slide to take only 2 arguments, the 2 arrays. But it takes something else, which is this type information. This type information is required, as you can see below, to get the unqualified type and the size of each element so that it knows how much to allocate. The next line just extends the X array with however many elements are in Y so that they fit everything. So then take a look at the arguments. They were usually typed arrays with like, I don't know, types of classes or structs, whatever they are. But now it just uses byte arrays because the type information is included in this TypeInfo argument. And the thing to note is that all this type information is extracted at runtime. So this is a function that runs and it asks, hey, what's the size of this type when it runs? But in fact, keep in mind that the compiler knows all this, everything that's in this square, oh, it's not a square, it's a rectangle actually, or everything that's in this rectangle is known by the compiler when generating this code. So this rectangle might not as well be there and save us some valuable runtime, as we're going to see in the end. Okay, so we talked about the arguments. The return type is also a void type because this was a precompiled hook. So imagine that all this library was precompiled before any D code would interface with it, which meant that it had to take any sort of arrays. And to implement generic types before the introduction of templates, you'd use void arrays. Okay, then this is the actual meat of the hook. It copies the content from one place to another, then applies the post blitz. Do you see anything wrong with this or anything missing from this approach? I mean, it calls the post blitz, but what's missing? Sorry? Copy constructor. Exactly. So it did not support copy constructors, which is a problem. So if you're using a structure with a copy constructor or a class that had a copy constructor, well, tough luck. Okay. So to put them all into perspective, most of this code is problematic. So we're going to fix it with our approach. First, let's look at it from the top. The D code remains the same. We don't want to break existing code. But then what we're going to do is to move the hook instantiation into the semantic analysis phase. Now, notice that the hooks have changed their signature. So now they're templates, which is the final part of the title of this presentation. And I'm going to explain why templates. One neat thing that we're also covering with this is that now we don't need to import all hooks into the resulting binary. We can just extract those that are actually needed. So now let's look at the meat again with the updated template hook, and quite a lot of things have changed. First of all, the arguments now have actual types, which means that they can specialize and, I don't know, possibly optimized if the compiler wishes to do so for specific types of the application. But then what's interesting is that all these constructions, unqualified in size of, that I highlighted down below, are now obtained by the compiler at compile time. So the runtime doesn't pay a penalty for this. You pay a small penalty at compile time, which I'll show at the end. But we also gain something else. A lot more flexible type information. So we can now ask the type if it has a copy constructor and use it, implement code that makes use of it. And of course, we don't forget about post blitz. We treat those as before. Okay, so this kind of fixes the problems with the existing code, but let's see what other problems it might introduce. So one example that I wish to focus on to draw most of the lessons from these three symmetry order of codes were comma expressions. Namely, the way they're used and the way that they've helped me do a better job at lowering these things. Because they all have to do with comma expressions. That was the funny thing, that whenever there was a comma expression, there was something that would break or something that I needed to change in order to do all this in a better way. So let's look at this code, which is very similar to what I've just shown you. If you're going to concatenate two arrays, it's pretty simple. You just call the hook that I've just shown. If you're going to concatenate a single element into an array, well, then you need to do it a little bit differently. You want to extend that array by one element, which is what happens here. Then you want to place your new element into the last position of that array, which is just extended. And then you want to return the original array so that you keep the type of the expression the same as it was supposed to. Okay, but all this needs to happen as a replacement of the code above. So what the compiler does is it calls all this chain of expressions a comma expression, because it's like a list of expressions with a comma between them. It's quite self-explanatory. Okay, let's see a case where this approach isn't correct, to be fair. So what has changed so far is that the array isn't just a regular variable, but it's a function call. If you apply the same logic as before, what you'll do is you'll call this function when you want to make your concatenation, but look how. You'll actually end up calling it 3 times. Once to extend the array, the second one to place your new element, and the third time to return it, which will cause the final assert to fail, because if you look at the function itself, it actually has a side effect of incrementing that pesky counter that would cause those asserts to fail. The solution here is to just save the result of this foo function into a temporary, like this. So first you save it, you call the function once, you have the pointer to the array stored in that temporary, and then you just use that temporary wherever you need it, and then it's fine. Okay, this is not particularly interesting, but things will get interesting from here. So let's take this function. This function is not particularly pesky at this point. What it does is the constructor saves a pointer to a global variable, which is val, into an internal pointer. Okay, and then it allows you to modify that global variable via this pointer. I mean, Dennis touched upon this earlier with Voldemort type. This is precisely what's going on there. C is basically a Voldemort type outside the no evil function. So what would happen in the case of new C is you'd also use a common expression. One that would allocate the memory for the object, the C object, by using the new class. This is the name of the hook. And then it would call the constructor that would set the pointer to the required global variable and so on. Okay, there's nothing special going on here. But let's see if you notice the difference between the evil and the no evil function. Do you notice what changes? Take a look at the no evil function now and see what changes when I move over to the evil function. What does it do differently? Exactly. So now val is a local variable on the stack on the evil stack. Okay, but because you assign a pointer to it, which you then modify, and this code works, which you then modify in the main function, then val needs to escape its lifetime, which is just the lifetime of the evil function, and to continue living until C is freed. So the way this thing is handled is via what's called as context pointers. Specifically, when the new C is returned, the whole stack of its scope is copied onto the heap together with the C object, so that the value of val is preserved within that stack frame. I said the whole stack, sorry, the whole stack frame of evil, that's what's copied. Okay, and C gets another hidden field called vthis. This is the context pointer that just points to the beginning of this stack frame that's saved on the heap in order for us to be able to access val. Okay. So basically, C now looks like this. Obviously, we don't write the code for vthis. This is just what the compiler introduces behind our backs and stabs us in the back in doing so. But it's just the way to preserve the lifetime of val beyond the length of its scope. So now let's see what this would do to our lowering. So let's try to lower this. So now we need to add information about this context pointer when doing our lowering. Fine, but let's go a little bit back to the approach we had to lowering. So at the beginning, all lowering was done in the semantic phase, which means that you start with a high-level expression, this time is new C. Okay, then you need to create this comma expression. To create this, basically, you would put all these together within your common expression, and then the IR generator would simply need to convert whatever it finds there to an actual IR representation. The problem is that there's no tooling in the front end to cover the context pointer. The IR generator is equipped with this, and it was usually the one that did all this context pointer magic, but the front end didn't. So at this point, we could either reinvent the wheel and move the context pointer logic from the IR generator to the semantic phase, or we could simply just use the existing code. And the same thing to do at this point was to use the existing code. So what it was doing previously is that the IR generator would take over all of this. So it would handle the context pointer on itself, create its own common expression by using lcombine, is the exact same thing as creating a common expression in the front end. And then it would call the non-template hook. Notice that it uses this TypeInfo class structure to get the type information that I mentioned at the beginning. From those 4 steps, the only one that's actually causing pain to us is the first one. The other 2 are perfectly fine. They don't use any type information, so we can just leave them there. We get no benefit if we move them over to the semantic phase just so we have the lowering in one place. So what we noticed at this point is that what we needed to do is to just handle the instantiation of the new class template into the semantic phase and then leave everything else for the IR generator. And this is a sleeker design that we came up with last year that would create, let's say, a partial lowering in the semantic phase just with the hook that's needed to allocate the memory for the class. And then the IR generator would use this hook for the first part of this common expression and then do its own thing that it was designed to do for the latter. Calling the constructor is easy to do in both cases, so that's not the problem. The context pointer was actually the pain. Okay, so this is what was changed in 2022 as opposed to 2021. In my first symmetry order of code, everything was done in the semantic phase. And this added some extra problems with CTFE. So when you interpret code, let's go over another example here, which just creates array A as a copy of array B. Notice that S has a post bit, so you'd need some sort of elaborate copying. You can't just memcopy it. And we have this static assert at the end to make sure that we have to run this foo function at compile time. Okay, so the high-level expression is the same as the one on the left, and the hook for this job is the array constructor. So since our first implementation was to replace the entire AST node, so think of the node up here, the high-level expression, it was completely replaced with the call to the hook. This left us nothing to do at CTFE, because this hook was calling allocator functions. It might call the GC, it might call malloc, depending on the situation. So this hook was not interpretable, which meant that CTFE couldn't really handle such situations. So what we did at first was we recreated the original expression here just for the sake of it having been interpreted, and then keep feeding the lowered expression to the IR generator. Okay, this is ugly on one hand because we have an AST node, we get rid of it, then we recreate it for interpretation, then we get rid of it again, all the while carrying this lowered expression. But what we tried to achieve here was to just remove the need to add an extra field to the initial AST node, so like a lowering field or something. We wanted to get rid of, to not do this, to keep the size of the AST nodes as small as possible. But another downside from this approach that Ian pointed out is that there are various optimizations that happened in GDC where expressions need to be in their original form when they enter the IR generator layer, and we were kind of skipping them by going with this approach. Another thing that we gained from this is a somewhat cleaner interpretation logic, meaning that now, well, actually starting from last year, from the last symmetry order of code, which was 2 years ago, you get the point, we added this extra lowering field to the expressions that require it. CTFE would just get the initial node, but now we no longer delete it, we just keep it there, and then the IR generator would do its magic with the lowering field and not interfere with the rest. Okay, so this is once again the split lowering approach that paid dividends to us in this regard. Okay, now let's go over the change. The biggest change that happened from the first two symmetry order of codes to the one that ended this year. So let's take another example, this time with array literals. So don't think of these as simple array concatenations. This is a concatenation of array literals. If you write the specific code, the compiler would obviously break it into a concatenation node with its children being the 1 to 3 literal on the left-hand side and the 4, 5 literal on the right-hand side. Okay, semantic analysis would just pick these two literals, create the lowerings for them, which are array literal tx. What this does is it just allocates the memory for the array. Copying the elements into the array, like putting 1, 2, 3 there, is handled by the IR generator. We've talked about this. We don't need to do all the work in the semantic phase. I mean, we're beyond that. But what happened afterwards is that the optimization phases and constant folding come after semantic analysis. That's the point. What they do is they change the original expression, the concatenation of the two arrays, into their result, because there's no point in running code that actually does a concatenation that you can do at compile time very easily. It's just like adding two numbers. Okay, but because this happens after semantic analysis, and because the two operand arrays have already been analyzed, there's no need to analyze the resulting array. So if 1, 2, 3 is fine in its context, so if its type checks with whatever it's used for, same goes for 4, 5, then there's no need to type check 1, 2, 3, 4, 5 again. You can just transfer the types that you've already established for 1, 2, 3, and there should be 4, 5 on the right-hand side. So you can just transfer the types of the two arrays onto the new resulting array, and then you're done. You don't have to run semantic on it again. which is a nice thing from the compiler's perspective, a really bad thing from a lowering perspective. Because now the lowering would, one, have to look for all the places where optimizations and foldings and whatnot would happen and replace those with the required hooks, or simply find a way to tap into the old hooks and then make them point to this one. It was getting messy. So, of course, at this point, the IR generator would find a new expression that has no hook set to it because nobody could, and then it would break at this point. It would give us a segfault. I already talked about one possible approach, which was to make the compiler inspect every array literal that it found or it generated somehow, and it updated its lowering. But then you would have to constantly re-lower array literals for no reason. Think of it like, what if you have array 1 concatenated with array 2, with array 3, and so on and so forth, I don't know, a few hundred times. Then you would just generate endless lowerings that wouldn't end up being used. Only the last one would be used. So the proposal that we made is to have something like this done. Basically to introduce a new pass. The high-level expression will be handled in the same way. We don't want to change that. There's no need to. But the semantic analysis would now do its type checking and everything, but it would just track now the required nodes that needed this sort of lowering. Then the optimization phases would do the folding and would create the final array, and they would update the tracking, namely tell our tracker to no longer look for 1, 2, 3, but to look for 1, 2, 3, 4, 5. Okay, then what we propose is another compiler pass after the AST is final, so no more changes to it, all the data is there, and this is what's going to be fed into the IR generator. And this lowering compiler pass would finally have all the information, all the final information we need for our hooks. Then it would just be fed to the IR generator and everyone would be happy. Well, this is still in the works because what happens at this point is that the lowering pass still needs to run semantic analysis on this hook. So you have to go back to step 2 and then all the way back to the fourth step in order to make sure everything's properly instantiated. This created some issues because in order to run semantic analysis, you need scope information. Well, tough luck, because scope information is only needed during semantic. So it's not something that's permanent. It's not something that's stored in the AST nodes. It's a stack of scopes that only exists during the semantic phase, and then it's destroyed. So what we're doing now is we're trying to save this in a stack of scopes and to make them available during the later phase, which is the lowering phase, and then use it from there. And we're having various sorts of bugs at this point that we're trying to fix. Okay, so this is what we're proposing now. It would get rid of many of the hacks that we've had to do and many of the multiple insertions of hooks that would be needed otherwise. But the scope information is kind of stabbing us in the back at this point. So let's look at what hooks I've worked on so far and how many of them have been converted, to templates. So during 2021, I picked up the work of Wild, who was a contributor to D, I think in 2019, if I remember correctly, for the Google Summer of Code or something. And I finished some of his work with these hooks. Then in 2022, I looked over more hooks and managed to convert those in the second rectangle to templates. And then came 2023 with a new batch of hooks and array literal, which is still in the works. So now in the future, what needs to be done is to take care of associative arrays, which aren't just one hook. I put it there just so I can fit all of this in one slide. What happens is associative arrays actually use an entire module in DRuntime, so everything there from hashing to accessing a single element to updating and everything, all of these need to be templated because all of these use TypeInfo, which is kind of unfortunate, but it also makes this particular endeavor a little bit more self-contained. Okay, so now let's look at some of the results that we've had so far. Basically, what we've done is we have both granular benchmarks for individual hooks, but then we wanted to coalesce all the hook arrays into a single larger benchmark. What this does is it instantiates an array, it copies it using DRA constructor. It then concatenates it. It then creates a literal array. Basically, it goes through all the hooks and adds code that would introduce each of them individually. This is kind of synthetic. We just wanted to see how well it works when we combined multiple hooks that we worked on. And our performance benefit is quite large. I mean, we get like from, let's say, around 20%. We used 3 types of arrays, very small ones, then medium ones like 64 elements, and the largest one was 256, and 3 types of structures just to make sure it scales well when you increase the sizes of these. All my benchmarks are open source. They're also written in D. I use mixins, for which I'm extremely grateful. Like they are one neat feature of D that helped me write very little code for these. But there's also a downside whenever you make the compiler somewhat more complex, which is that you will increase compilation times. So what happened at this point, we took like 3 projects and we wanted to see how much they've changed. Keep in mind that these changes were between 2 checkpoints. We didn't check the increase in compilation times between individual hooks because we saw no sizable difference in this. The margin of error was usually larger than the difference between individual runs and between the 2 approaches. So Dscanner's compilation time increased by 24%, and everyone else was kind of in between. What I would like to say is that these are quite coarse measurements because we just took a snapshot in 2021, then another one in 2023 towards the end. But there were many changes to the compiler and to these projects themselves, so we don't exactly know how much of this was caused by our hooks and how much was caused by other factors. We just noticed that this increase, and to a certain extent, our hooks would play a role in this. Okay, the main takeaways at this point are that, to be fair, my first symmetry of code, my first contact with D was in 2021. Starting my master's project, I just mainly explored the compiler. I learned how things were done in a real-world compiler, and this gave me a lot of confidence in myself that I could actually do some work and receive feedback and drive things to completion. 2022 was more about, let's say, fine-tuning what I had already done. Put the lowerings into a separate field, get more feedback and get more work done. And then 2023 was kind of about making something possibly groundbreaking, but I didn't get to finish it till the end, which is to propose a new compiler pass that would hopefully, in our opinion, alleviate some of the pains that we've been having throughout these 3 editions of Asymmetry of code. So this has been my talk. I'm intentionally leaving it here just to get some more feedback on, I don't know, the new compiler pass and what you think of this story that I told you. So go ahead, shoot. Thank you.
So regarding the increase in compile time, why was, probably a question for Walter, by the way, why were this logic, lowering logic, implemented in the first place in the compiler? Why isn't this logic initially implemented directly in the compiler without the DRuntime hooks?
Wait a second. So what was the question? Why was the logic implemented in the compiler, or what? Where else?
Yeah, why are we having this extra layer of templates in the DRuntime instead of having these implementations of the operations implemented directly in the compiler source?
Oh, okay, makes sense. Well, think of let's go over this example. So imagine all of this. The compiler will have to generate code like this, which can be very tedious. It would just have to insert all these extra calls to functions, to memcopy, to call the post blitz, when it can just call one function. It's much more convenient for the compiler to have to only take care of one thing, which is to call this hook, DRA append, rather than worry about inserting all this code. So in fact, it reduces the complexity of the compiler when you have runtime hooks that take care of higher level expressions, which are more complex and difficult to handle and code generate than A plus B, something. Than to generate this code manually, line by line, so to speak. And Walter, if you have a better answer, please do.
That's exactly correct.
Thank you.
Did you look at code size? Did you look at how your changes made the binary larger or not?
Yeah, that's a good question. So our first task, or let's say our first objective, was to possibly run D on microcontrollers and stuff like that, so on embedded systems. We didn't actually get to do that. We focused more on performance and on compile times. And the thing is, you can have, let's say, two things happening at the same time which might cancel each other out. On one hand, you get fewer hooks into the resulting binary, possibly. Fewer separate hooks. But what you can have is more instances of the same hook, because when you instantiate templates, what happens is that if you use DArray append with, let's say, integer arrays, you'd have one instance of this template. If you use DRuntime append with some class arrays, then you'd have another instance of it. So you might run into template explosion, but we haven't had the time to explore this. But this is a very fair point, and we should worry about it.
There's been some ports of the DRuntime to a few different environments. Hypreme did one. I think ADR did one. There's been some others out there. I just wonder if you'd had any interaction with kind of the other ones that have been out there, and have they requested features, or has their life been improved? Do you anticipate more, ports of the runtime? Basically, just what's happening in the surrounding target environment for DRuntime.
Okay, well, let's have an ideal scenario where the entire runtime is using templates. We're far from that, but let's think big for a second. Then porting would actually make it slightly easier, because you wouldn't have to compile it separately for different architectures of different targets. You just have to compile your code, and then the compiler for the code would take the code from the runtime library as if it were code in your application. So you would reduce the complexity a little bit. You just need to compile your application, and that would also get you the required code from the runtime. Does that answer your question? Perhaps I didn't understand.
Yeah, I think so. For example, you've talked to Marcelo about his port, and you kind of understand what your clients might want from you, and you think you're covering it, I guess is what you're saying. You think that you're going to get there.
Yes.
Looks like we're done.
Okay, thank you.